Why?
completed. So I couldn't. I was given work from school actually for chemistry. So
You people used to consider the work given by the school to be like that you had really done something after doing that.
like as in,
Like there is any kind of a work that is being given to you from by the school. Do you really think that that really helps you in anything except the marks that you get from the school?
mm,
I actually used to think that whatever the thing that school assigns to school used to assign me, that it was really like that. I used to just do it as it is because that doesn't matter. That does not help in that is
yeah,
not the real learning. They used to just give some assignments or something that we used to just
yeah,
actually most of us used to copy paste it from one place to another. So that is just helping us to improve our writing. That's it. Okay, so don't
yes,
consider that work as that you had learned something from that. That means consider it that you had not done anything on that particular day. Okay.
yes.
Yes, what were we doing in the last class?
Also, we did self-inductance.
We had completed till the self-inductance. And after that self-inductance, what have we reached till any expression for to find
Yeah,
out
we
the
had
self-inductance?
reached.
Yes. What was that particular thing?
Sir, that was. Sir, I had not taken note of that. The last
Yes, Rehan.
expression.
Yeah. They didn't send the note. Like we asked for the notes, but they didn't send the notes, so I wasn't able to write. But like I think it's uh we
I
found
don't know
the
that what is true and what is not. Okay. So tell me one thing
No,
that
sir, they did not send the notes. I didn't get the notes.
N phi equals to Li. Have we written this in the last class?
Oh, yes, yes, sir.
yeah this we
What
have.
was happening actually? This was the n times of loops. We were talking about the inductor, so this was the thing. And what we had said that flux through the total flux was depending over the current I. And by that, what we did, we placed the sign of equality for to remove this proportionality and had placed it like this: n phi equals to Li. Yes or no?
Yes,
Yeah.
sir.
And by after that, what we had did, we for to find the EMF induced. If the flux changes, that means the EMF will be induced. And what we did minus of d by dt of n phi. Yes or no? The total
Yes,
flux
sir.
rate of change of flux. Then we'll place a minus sign outside, and instead of n phi, I'm just writing it Li over here. And
Yes, sir.
what the next I'll do? Minus of L times of di by dt because L is the constant one. Okay, have we
Yes, sir.
reached till this
Yeah.
expression that we had got EMF equals to minus of L times of di by dt, and this is actually the potential difference across the inductor. This is the potential difference across the inductor. Like, what? Just tell me one thing that if we take a resistance like this, and if I current is passing through it, this is the resistance R. What is the potential difference across it? V equals to
Higher.
Iron.
IR, or why do if I am writing it in terms of EMF, I'll say it E equals
Yeah.
to or whatever V equals to I into R. Is this okay? And if
Yes, sir.
I'm writing this for the resistance, but for the inductor, what is happening? If the current is changing, then only EMF will be induced across it. And that EMF or the voltage
Mm,
across induced will be minus of L times of di by dt. Is this clear to you?
yes, sir.
Yes, sir.
That's why that is the reason why we you always see the inductor to be get joined with the AC circuits only. You will get it.
Yes.
You will never. Why? Because the current is changing in
Very.
this, and because of that, V is being established there. Understood? Yes, Rijan.
Yes.
Yes.
Okay. You will
Okay.
never see it like that. The inductor is joined with the battery like this. Why?
Mm.
Because this do not provide the variable current. And as the current will not change, so the EMF will not be induced across the inductor. Do you people agree with this?
Yes,
Yes,
sir.
sir.
Okay, so this was the thing that we had seen in the last class. And till this point we had already covered. So actually till now we had got the two expression. One is EMF equals to minus of LDI by dt, and the second one is N phi equals to Li. Yes or no?
Yes, sir.
These were the two things that was most important for us while doing the calculations or anything, and we had got till here. Okay, and from the, if we had got the EMF, so we can divide it by the resistance and we can get the current also. Okay.
Yes, sir.
Okay, so now what is going to happen, that we are going to define this self inductance. Till now what we had said that it is a constant. Till now what we had said that it is a constant, but how we actually used to define it. So we can we can actually do it by two means. So let me do it over here. Okay, so now from now onwards we are starting the 2ds content, that is the self inductance. Okay, self inductance, or we also used to say this as a coefficient of self inductance.
Yep.
Understood? This is we had done, and we actually used to define it in the two ways. So let me make a separate line over here, and then we'll define. One is like we already know that this, that N phi equals to Li. Actually, you must be clear about what the it is. What is N? Yes, Region, what is N?
Total number of turns.
And what is phi, Health?
5 is the total flux
Phi is the
in
total flux.
in one
Yes,
turn,
in one of the ring. And
Yes.
what is N phi? N phi is the total number of flux, total flux linked with particular coil. Okay, L is
Yes.
the coefficient of self-inductance, and I is the current passing through it. We can define it like this also, or we can define it like we had just said, that EMF equals to minus of L times of di by dt. Yes or no? Can we say it like this also?
Yes.
Or what we can say, if we want to define the L from this particular expression, what I need to do? I need to do N phi by I. Yes or no?
Yes.
Okay, and what the next, if I define L from here, what I am doing, minus of E divided by di by dt. This is not important, this is just for the defining purpose, that how we actually used to define it. Okay.
Yes, sir.
Okay, now tell me, if I equals to 1 ampere, I is equals to 1 ampere, so do you believe that the coefficient of self inductance will become numerically equal to the total flux linked with the coil? Yes or
Yes.
no? So
Yes.
this is the thing, that how we used to define that when the current passing through the particular coil is 1 ampere, then the self-inductance will become numerically equal to the total flux passing through it. Okay, why I'm using this word numerically equal? Because the unit of flux and the L is different. Okay, the unit of L
Yes.
is, yes, Rijan, what is the unit of L?
Yeah. Uh,
Yes, Sahil.
Oh, sir, I was going to ask that question. What was the unit of L?
Can you define it from, what is the unit of flux?
Weaver.
Flux
Weber.
is Weber. Weber, right?
Weber. And what is the current?
A.
Ampere.
Weber per ampere. You can define it like this. Or what can you
Uh,
say? You can also say, have I told you about this word?
no, no.
Hmm.
No. Have I not said use the word Henry in the class?
Oh, yes. Yes. But not like,
Yes, I
sir,
had
you're
just
talking about
told you
last
once.
class?
Yes, in the last
Or
class, I had said this
no?
word Henry,
Oh,
and I just moved away. I had not invested a lot of time over it. Okay,
oh, okay,
so
sir.
in the
Yes, sir.
unit of inductor is L is Henry actually. Weber per ampere is also one, but we used to use the word Henry. Okay. So
Okay, sir.
what we should write here, if I is equals to 1 ampere, self-inductance, self-inductance, self-inductance will become, or is numerically equal to the total magnetic flux, linked in linked with coil. Total magnetic flux linked with coil. Okay, understood?
Yes, sir.
Okay, or we can also say that total magnetic flux linked with the coil, or just linked with the inductor, whatever you want. Okay, in this case, what do you believe that tell me one thing, that if rate of change of current with time, rate of change of current, that means whenever I'm using the word rate, that means I'm looking for its change with time. Rate means divided by time.
Yes.
Okay, so if I'm saying rate of change of current is 1 ampere per second, then L will become equal to E. Yes or no? By magnitude wise. Okay, let me do one thing. Let me do now. Instead of this, I'm just looking for its magnitude. Okay, so we'll remove the minus sign from here. Okay, so what can we say about that? If the di by dt, rate of change of current, is 1 ampere per second, if di by dt equals to 1 ampere per second, so L will become equal to E. Yes or
Total
no?
EMF. Yes,
Yes.
sir.
Self inductance is numerically equal to the induced EMF in the inductor if rate of change of current through it is 1 ampere per second. Yes or no? Is this clear to
Yes.
you,
Yes,
both
sir.
of you? So this is one of the
Yes,
things
sir.
that how we used to define the self-inductance, and that's all about this. Okay, and the next thing that now we'll look for, that how we can actually calculate it. Now actually what we are going to look for, that calculation of self-inductance. Calculation of self-inductance. Now we are going to calculate that how that what is actually the self-inductance. Okay, so let's say that we have a coil somewhat like this. Okay, inductor that is somewhat like this, and let's say it is having a total length of L and having the let's divide it with capital. Okay, this is, and what is the N? N is the total number of turn. Total number of turn. Okay, what is this small n? Small n is capital N by capital L. That is number of turns per unit length. Number of turns per unit or per unit length. Is this okay to you?
Yes.
Yes, sir.
Okay, so this is that. Now what can I say? Now I'm going to see that how much flux is being leaked. Suppose from one of the loop, the phi flux is being leaked. So what can I say right here? That n phi equals to Li. Yes or no? Can I
Yes.
write it
Yes,
over
sir.
here? If I can write it, so can I write L to be equal to n phi by I? Yes or no?
Yes, sir.
Yes, sir.
Now tell me one thing, that what this phi is equal to. Phi is equal to the magnetic flux. Yes or no?
Yes.
And how we
Yes.
used to define the flux? Okay, do we used to define it with B into A?
Yes.
Okay,
Yes,
so
sir.
what we are going to do, NBA by I. Can we say it like this?
Yeah. Yes, sir.
And
Yes.
suppose if I current is flowing into it, what is happening? I current is flowing inside it. So can you tell me that how much? And this is very long solenoid actually. Okay, what I'm considering over here, that this is a very long solenoid. So how much magnetic field is inside it? What is the B inside
Mu
it?
naught and I.
Mu naught n I, capital N or small n?
Small n.
Mu naught n I. So this is the something that we can say here. So can we place it over here also? L equals to n. Instead of B, what I can write? Mu naught small n into I. Yes or no? And I can write the area to be like this and divided by I. Yes or no?
Yes, sir.
So do you agree that this will be
I
cancelled
gets
out by
cancelled.
this?
Yes.
So have are we getting the answer L equals to n, or let me write it a little properly, mu naught small n capital N by A? Yes or no?
You write it as n square upon L, right?
Can we write it as n square? Oh, okay, okay, okay. You are,
Upon L.
what are you saying? That he's saying that we can replace this capital N by number of turns per unit length into total length. You are saying to
Yeah.
replace it somewhat like this, not a small n, no?
No.
That is this.
Yeah.
Okay, and yes, that's why I had chosen the small n there, small l over there. Okay, so that will be mu naught small n into, instead of capital N, what I can write? I can write n into L. Yes or no? Into A.
Yes, sir.
Yes.
So can you see? Is it looking like mu naught n square A into L?
Yes.
This is quite impressive and quite very nice expression that we had received. Why I'm saying so? Because we can see what this A into L expresses. Is it not the volume of this particular solenoid?
Yes. Yes.
Area of cross section into length.
Yes, sir.
So can we write it like that? L equals to mu naught n square into volume.
Yes.
Yes or no? And this is the
Yes.
expression
Yes.
that I can remember easily. Is this
Yes,
clear
sir.
to you? So this is
Yes,
the
sir.
something that you must remember about, that the self inductance of an inductor is mu naught n square into volume. What is mu naught? Mu naught is, what is mu naught?
4 pi
Mu
into
naught is 4 pi
4
into
pi
10 raised to
into
minus
10 to the
7.
power minus
this
7.
one.
And check out the SI unit, whatever it is, whatever the SI unit.
Uh,
Mm.
Sorry, what is the SI unit of this? You can define it in any way. You can define it in any way. You can define it like Henry per, what will be the mu naught from this expression? You will get it as Henry
sorry.
per meter cube. Yes or no?
Yes.
You can get it
Yes,
like
sir.
this also. Okay, so you can write it as it is, Henry per meter cube. Actually, I don't also used to remember it, because it is used according to the question. If the question is giving this particular unit, you should use this, or in whatever the term it is being used. Acha, tell me one thing, that if I replace the material inside it, if I replace the material inside it, this mu naught is material dependent. This
Yes.
mu naught is depending over the, what is it?
Material.
It is depending over the environment or the material inside solenoid. What we used to say, it is the permeability. Yes or no? Permeability of free space. Or do we used to say it
Yes.
as mu naught? It is the permeability of free space. But
Yes,
if,
sir.
let's say, we have a different material, if we are placing somewhat different material inside the solenoid like this, understood? And if it is a different material, so its relative permeability mu r will be given to you. And if mu r is
Yes,
given
sir.
to you, now instead of mu naught, you should use mu. That will be given by mu r into mu naught. Understood?
Yeah,
Yes, sir.
yes, sir.
You should use this particular expression instead of that particular thing. You should use this here. Okay, as it is air, so mu r is 1 there. Mu r is 1, and that's why mu is becoming equal to the mu naught. Is this clear to both of you?
Yes,
Yes,
sir.
sir.
So this is one of the thing that we used to do, and this expression can be written in terms of somewhat different also if you replace the small n by capital N by L. So that will become some different. You understood that what I mean to say? You can replace this n by L also.
Yeah, then
Okay,
you'll,
and you
yes,
will get a somewhat different expression, but not need to remember that. Just remember this one. This is somewhat the important one, that is mu naught equals to n square by volume, n square into volume. Okay.
yes, sir.
So
Yes, sir.
this is the one thing that you should know about. The next thing that what we can see from here is what we can see here, that we had derived that L is equals to what we had derived from here, that L is become equal to mu naught. Instead of
Yes,
mu
sir.
naught, let's write mu here, mu naught N square into volume. Yes or no? And instead of volume, let us write it explicitly, A into L.
Yeah.
Okay, we had seen this. So can we see that sorry, that self inductance of of an inductor depends on the number of turns? Yes or no?
Yes.
Yes, sir.
Yes, sir.
It depends also over the length of the inductor.
Yes, sir.
Yes,
It depends on the area of cross section of the particular inductor.
Yes, sir.
It
yes,
depends on the medium inside it.
Um,
yes,
yes, sir.
Okay, so you should see that what I can write here, self inductance. Self inductance depends over the first thing that we will write here is that number of turns, that will write capital N, length of inductor, that is capital small L, that second third is area. Okay, that is A. The next is fourth one, that is the medium inside the inductor. And can you see that if we place the any material inside it, the self inductance of the inductor will increase.
yes, yes, sir.
Okay, the self inductance of the material will get increased. So actually,
Yes,
while when we use it in a practical situation, we used to place a medium inside it. Okay, so that the self inductance of that material is being increased. Okay, we
yes, sir.
can also say that okay, let it be like from this only. Okay, so this is the self inductance that was depending over this. Okay, is this clear to you?
Yes, sir.
Yes, sir.
Okay, now we can also some of the easy things that you should know about, but let me plot it over here. Let's suppose that if I'm writing the flux at this side and I at this side, what kind of graph do you expect?
Uh, so it will be a linear graph, right?
It will be a linear graph. Yes, Rijan, do you also expect that?
Yes, sir.
And what will be the slope of this graph?
Tan theta,
Positive. Oh, yeah.
tan phi,
If I say,
yes,
let's not put the phi
yeah,
here, let's place the
yes.
theta here. So if I ask the tan theta, yes, Rijan, what it will be equal to?
Uh, yeah. L by theta.
Can you see that flux is equals
Oh,
to L into I?
yes.
So is it looking like y equals to mx? That instead of place of x, I
Tan
and
theta
phi
will be
is
L,
just placed by y. Tan theta will be equal to L. That will be
L.
that is the slope of this graph.
yes,
Oh,
Is this clear
okay.
to both of you?
Yes, sir.
So you
yes,
must know about it. Okay. Now what next I'm going to do here is that suppose now my next aim is to calculate the energy inside the inductor. Energy stored inside the inductor. Now I'm going to calculate the energy stored inside the inductor. So what kind of inductor do we have? We have somewhat the inductor looking like this. Yes or no?
Yes, yes, sir.
And let's say, do you agree that if a constant current is passing through it, so no EMF will be induced across it?
Yes, sir.
That means the current that should pass through it should be variable with time. Do you agree with this, region?
Yes, sir.
Then only what is going to happen? The flux through the loop is going to
Close
change
those.
and the EMF will be induced. Okay. So let's
Yeah.
say that I of t, that's why I'm taking it to be a variable. Okay. So I of t is the current passing through it. And let's say it is the E of t that is being induced across it. It is the E of t that is being induced across it. So if I calculate the power P of t, do you agree that it will be nothing but I of t into E of t?
Yes, sir.
Uh,
Yes.
like see, if I'm writing it like this, I of t and E of t, it will become a little congested. That's why I'm rewriting this particular expression in terms of simply P equals to I into E. But keep in this mind that all these are depending over the time. It is variable.
Yes, sir.
Okay.
Okay.
Now tell me one thing, that this E is equals to,
P by. Oh no.
in terms of inductor L. Yes, region.
Li.
Yeah. What?
EMF will be equal to, in terms of inductor L, will be equal to, I just told you above.
Oh yeah, minus L derivative.
What's that?
Yes or no? Will it be this or not? You should
Yes.
keep writing this, at least formula, all these things right now. Okay,
Yes.
and
Mm.
complete notes will be provided to you after the class. So write it after that, but before it, just write it like this only. EMF E equals to minus of L times of di by dt. If it is like that, so what is going to happen? That you can, what do you, what actually we want to calculate? P into I into E. Yes or no?
Yes.
Yes.
So actually, if we write P to be like this, and let keep the I to be like this, and instead of E, okay, Acha, tell me one thing. If I calculate this at the end, I'm going to calculate the energy E. Yes or no?
Yeah. Yeah.
If I'm
Yes.
calculating the energy E, so does it, will it become negative? So will you accept that answer? Can energy be negative?
Mm.
No.
Energy cannot be negative. So you should not take care about the sign right now, that whether we are getting the positive answers or the negative answer. The whatever the answer we'll take, we'll always just take the magnitude of that. Okay.
Okay.
So
Okay, sir.
instead of E, let us take magnitude of E. Okay. And if we take the magnitude of E, it will be L times of di by dt. And I, and the E will be L times of di by dt. Yes or no?
Yes.
Yes, sir.
And instead of P, can I write it like dE by dt?
Yes.
I into L into di by dt. Is it correct? Any issues with this?
No, sir.
Can I cancel out this dt from both the sides?
Mm.
Yes.
And what else is being left? dE L I into di. Yes or no?
Yes, sir.
And if I integrate it to both the sides, what will I get? We'll just integrate it to a current I. Okay. And to E, EMF E, will I let it be E. Okay, so will it become E this side EMF, and what will be the integration of IDI? Yes, region.
I square.
I square by 2. I square by
Yeah. I
2.
square by
What will
2.
be the limit? 0 by 0 to I. So what will I get? Will I get half L I square?
Yes, sir.
Okay, understood? So this is the
Yes.
thing that you should know about, that energy stored in the inductor is nothing but half L I square.
Uh,
This
this
expression
is,
Yes, sir.
mm,
you must know about, that energy in the inductor is actually this is was energy now. Why I had drawn it like that? So
Mm.
this is that. So energy is it like this. Okay.
Yes.
Now
Yes, sir.
see, if you want to derive the unit of L from this expression, you will get it as joule per ampere square. है ना? So just derive it accordingly the question demands. So energy will be equal to half L I square. Is this clear to both of you?
Yes, sir.
Yes, sir.
Now you can rewrite this expression like you already know the L. So write it here and you will get a next expression. But no need to remember that. Just remember it separately that about all both the things. Is this clear to you?
Yes.
Yes, sir.
Okay. Now let us do calculation of magnetic energy density. This is one of the concept that will be used somewhere else also, but only the final expression that I'm going to get here after this, only that expression will be used there. So you should know about that how we are calculating it over here. Okay, the thing that we are going to calculate over here is magnetic energy density. So magnetic energy density means that how much energy is being spread over the volume. That means we'll see that energy per unit volume. What we are going to get here is that this is the inductor that we are going to have. Uh, Let me draw it a little properly. That this is the inductor that we are having, and we will try to find out the thing that what is the energy density in a uniform magnetic field. Okay, magnetic energy density in uniform magnetic field. Okay, in uniform magnetic field, uniform B. Okay. Actually, what used to happen inside it, the magnetic field is uniform. That is, are parallel lines. Yes or no? With a
Yes,
constant
sir.
one, that is mu naught and I. Do you know about it, Rijan? Yes or no?
Yes, sir.
It is inside it. Remember this particular expression that inside it, the magnetic field is mu naught and I. Okay. So now, if we want to derive the magnetic energy density formula, so do you agree that you want to calculate actually the energy per unit volume? Yes or no?
Yes.
And we actually used to define it by mu b. Okay, so if it is like that, so what is the energy of inductor? Can you tell me that what is the energy?
Oh,
That is
L I square.
half L
Uh,
I square. And what is the volume over here? What
uh,
should the volume should I take here?
into L.
A into L, exactly. Okay, this is the area of cross section that the A I'm taking, and this is the total length that is the L I'm taking over here. Okay, this is something, but it's okay. Is it it is the right answer, but I can represent it in somewhat a better manner, because what till now I'm watching here, what is the kinetic energy? That is half mv square. What is the energy stored in the inductor? That is half li square. So I always used to see the terms in terms of half and something square. Okay, it's my thing that I always used to see the things energy in terms of like this. So we will try to reduce it in that form. So what do you expect that what the change should I next do?
Like
Sir,
just
Yes, what should I do? Can I replace the L with
L,
the
yeah.
known quantity that I know? Because that contains the volume, and in the denominator I already
Yes.
have the volume that will get cancelled out.
So you can put mu naught and square.
Half what is the L? What is the self inductance of an inductor?
Mu naught and square
Into
and square
A into L
A to L.
volume,
Yes.
and I square it is that, and divided by A into L. Is it okay?
yes, sir.
Yes, sir.
And do you agree that this will cancel out each other?
Yes.
Yes, sir.
And what the final result that I'll get? That is half into mu naught n square into I square. Yes or no?
Yes, sir.
But still, the answer is too big to learn. Yes, this is the right answer, but still it is somewhat we can reduce it. How I can reduce it? Just multiply the mu naught in the numerator and the denominator. What the next thing that you will get? You will get half mu naught square n square into I square divided by mu naught. Yes or no?
Yes.
So do you agree that half mu naught n I is can be written in terms of whole square divided by mu naught? Yes or no?
Yes,
Yes,
sir.
sir.
Yes, Region. What is the term inside the bracket? What is this term?
Uh, is the magnetic field
Yes,
inside the
magnetic field
solenoid?
inside the solenoid. Okay,
Yeah, the
half
constant.
b square by mu naught. So this is the reduced expression, that is mu b equals to b square by 2 mu naught. Okay, is this clear to you?
Yes, sir.
Yes, sir.
That is b square by 2 mu naught. So you must know about this particular expression also. Is this clear to you? Again, the
Yes, sir.
same story, I will not repeat it again and again. We are considering the medium to be air. That's why I'm using this mu naught here. If the material is given to you, then you must take mu r also into the consideration. In that case, mu will become mu r into mu naught, and you will replace this mu naught with this mu. Is this clear to
Yes.
both of you?
Yes, sir.
Yes, sir.
What is R? It is the relative permeability. It will be given
Yes.
to you in the question. Okay, understood? And do you people, like, I don't, I'm not deriving it over here, but do you know also the energy density of electric field? Have you derived it?
Electric. Yes, sir. But
Was that half epsilon naught into E square?
yes.
Okay, so I'm not deriving it over here, but these are the two things that we used to see at most of the places, so we should keep this in mind. Okay, b square by 2 mu naught is it, and you will see that many of the people used to derive it. Many of the people used to derive the energy inside the inductor using this particular concept, that they used to say that the energy density is this. So if we multiply it with the volume of the inductor, we'll get the energy stored in the inductor. Do you agree with this or not? What is mu b? Mu b is the energy per unit volume. What it is? It is energy per unit volume.
Yes, sir.
Yes or no?
Yes.
Yes, sir.
So if we multiply this with the volume of the inductor, we'll get the energy stored in the inductor.
Yes.
Yes or no? So you can
Yes.
do that also. Like if you want to calculate the energy, what next you will do? You will do b square 2 into mu naught into volume. Volume is what? Volume is
A
A
into
into
L.
L. Okay. And what actually you want to derive it in terms of half L I square. Okay. Half is already there. Just replace the b in terms of mu naught and I, and you will get the result to be as expected, half L. You will see that mu naught n square into volume is it here. Can you see this? B square, if you will
Yes.
do the b square, you will get mu naught square n square into I whole square divided by 2 into mu naught. Yes or no?
Yes.
Yes, sir.
So what into A and L also will be there, na?
Yeah.
A and L
Yeah.
will also be there. Okay. Now, what is going to happen? Just replace it with the things and you will get the L to be here. What is L actually equal to? Mu naught n square into volume. Just cancel out
Yes.
this mu
Yes, sir.
naught from here. What you will get? The next thing that you will get here is 1 by 2 mu naught n square into A into L into I square. What this central term is looking like? Is it mu
Self
naught n square into
reference.
volume? This is the L. So half
Yes.
L I square again. Okay, so you can derive it in the reverse format also, but it's all your call that how the question demands. Sometimes what happens that if it is specifically written explicitly in the question that derive it using the formula of energy density, then you should go for this approach. Otherwise, you can do that particular one, that is the power and energy related things. Okay, understood?
Okay.
Yes, sir.
Now we are going to move over to the next topic, that is the last of this particular chapter, that is the mutual inductance. Okay, that is what we are going to learn, that is the mutual inductance. If we are going to see the mutual inductance, first of all let's see that what it is. Based over that, we'll see that what is happening over here. Suppose what is happening, that I'm taking the two loop. I'm taking the two loop. Suppose that the I2 is flowing here and I1 is flowing here. Okay.
Okay.
Or let's say that I1 is not flowing here. Let's say the I1 is not flowing over here. Let's say, okay, it is nothing but, okay, let it be like this. Now tell me one thing, that if I2 increases, if I2 increases, so do you agree that because of I2 the magnetic field is being uh, 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 magnetic field is being produced because of this moving current I2? Yes or no?
Yes.
Yes, sir.
And that magnetic field is passing through this loop also. Is
Yes.
it coming from first direction or the second one? What is the direction?
First direction. First direction.
First direction. How we are finding it out? Using the right
Right
hand thumb
hand.
rule. Keep the thumb in the direction of current. You will see that the magnetic field is pointed along the upward direction. Yes or no? If you will curl it, you will get the magnetic field is in the upward
Up.
direction. So what can we say? That the magnetic field is in upward direction. Now tell me one thing, that if the if I2 increases, B will also increase.
Yes. Correct.
Yes.
B will also increase. If the B will increase, do you agree that the flux through the central loop will change?
Ye- Yes.
Yes.
And because of that, the EMF will be induced in it.
Mm. Okay.
Yes.
So do you agree that because of because of the change in current in the one loop, the flux is being
Mm.
induced in the another loop?
Yes.
Yes.
So this is actually what the mutual inductance relate. Understood? This is
Yes, sir.
we are going to see the relation of this kind of something. Okay, understood?
Yes.
Okay,
Yes, sir.
so write it over here, or let me just a second. Yes. Okay, so what we're saying, that mutual inductance, we are saying somewhat like this, that if the current through one of the loop changes, the flux through the another loop changes and the EMF is induced in that. Okay, and this phenomena is actually said to be as mutual inductance. Okay, so what we can write here is that the phenomena of production of an induced EMF, the phenomena of production of an induced EMF and induced current, because the EMF is induced, so the current will also be induced in a coil. Current flows in another coil, which is kept very close to it, is known as mutual inductance. Understood?
Yes, sir.
This was the thing that I had said to you, that what is happening, that the production of induced EMF or induced current in a coil, when a current flows in another coil. Current was flowing in the another coil. Because of that change in the current, the flux through somewhat another coil has changed, and as a result, the EMF was being induced in it. Yes or no?
Yes.
Yes, sir.
What next we can write here? Due to, can we see that due to the current in primary coil, what we can say? We can say one coil to be the primary one and the another one to be the secondary one. Okay, we used to
Okay.
say that one current to be the primary one. Okay, let us assume this to be I1. So let us say that I1 is the primary coil. So the current through one of the coil, magnetic flux magnetic flux is linked with somewhat another coil. Okay, so what I can
Yes.
say right here is that due to the current flow in primary coil, magnetic flux will link with it. The same flux links with secondary coil. Okay, what we can write here is if this magnetic flux changes in the primary coil, in the primary coil, then induced EMF and induced current flows in secondary coil. Coil. Okay, so this is actually happening that if we are changing the, actually what is actually we had written all over here, that due to the current flow in the primary coil, we had considered the bigger coil to be the primary coil. Magnetic flux will link with it. Magnetic flux will link with the primary coil as well as the secondary coil. The same flux will be linked with the both the coils. What the reason behind that? See, if we are right saying this, that's why I had drawn this ring, this secondary ring, to be a very small. The reason behind that, because of this bigger coil, what is happening? There is the magnetic field, and actually, what is this magnetic field equal to? Yes, Ahil.
Uh, so mu naught I by 2 r at that point,
Mu
right?
naught I by 2r. But where it is? It is actually at the center.
Center is.
Yes or no? Yes, Rijan, do you know about it? That this magnetic field is actually mu naught I by 2r, but this magnetic field is only at the center. Let me write it with capital R. This magnetic field is situated at the center, and we are considering this to be small. We are considering this coil to be the small, so the flux through whole loop will be same. Okay, do you agree with this? B into, that's why we can multiply that. What I can say, that through the whole loop the same magnetic field is passing through. Otherwise, there will be a little variation. If I choose this coil to be somewhat bigger, so I don't know that what will be the magnetic field here and at the center. Only the center one is being known by me. The rest of the places will not be known by me. Understood?
Yes.
We actually
Yes.
used to discuss this in the chapter of magnetic field. We know the magnetic field only at the center. Okay, we don't know what is the magnetic field here. We don't know. Okay, we actually know this particular one, if the current is flowing in this direction. So this is the reason why I'm taking this to be the small. If I'm taking this to be the small, what I can consider, that throughout the loop the same magnetic field is being flowing. Okay, so that I can say that the same flux is linked with the secondary coil. And what I can say that in the secondary coil also the same flux will be linked. Whatever the flux is linked with the first one, the same flux will be linked with the second one also. The reason behind that, see, because of the second one, now it is the important discussion that we are doing here. We are considering this to be a bigger coil. Okay, now listen it very carefully. And we are considering, okay, for the time being, I'm drawing it big so that we can understand the things, but it is actually small. It is actually small. Okay, tell me one thing that we had already discussed it. Suppose this is the area A and somewhat magnetic field are passing through it. So what will I write the flux? I'll write it as B dot A, B into A. Okay, I'm just considering the angle to be 0 degree for the simplicity purpose, and I'm doing it like this. Yes or no? Yes, Rijan?
Yes, sir.
Okay. Now tell me one thing. If I choose a bigger area, if I
Yeah.
choose somewhat a bigger area, so will the flux change?
Yes.
Mm, what? Uh,
Only the magnetic field are drawn that I had drawn here. Only this is the magnetic field being
Oh,
situated
oh,
here.
oh, then no,
Flux is not going to change.
not going to
We had
change. Okay.
yeah.
already discussed it in the first class where we were calculating the flux. That flux do
Yeah.
not depend over
Yes,
the area.
Yeah. Yeah. Yeah.
yes,
If I had drawn the magnetic field at this place only, so even if I choose a bigger area, the flux is going to remain same for both the things.
Yes, sir.
yes, sir.
And that is the concept that I'm applying here, that through the primary coil, as well as this is I'm marking as the primary coil, and this is I'm marking as the secondary coil. Throughout from the primary coil as well as the secondary coil, the flux is going to remain same. That will be the B, because of this I2, because of this the magnetic field B, that is B2, into this small area A1. That is the flux going to remain same for both, as well as for one as well as for two. Understood?
Yes, sir.
Yes, sir.
Is this clear to you? So you must remember about these two things. That is why I had written what I had written here, that the same flux linked with the secondary coil also. Okay, the same
Okay.
flux linked with the secondary coil also. Is this clear to both of you?
Yes, sir.
Yes, sir.
So what I can write here, that the flux, the flux through the secondary coil is directly proportional to the current in the primary coil. Can I write it like this? As I increase the current in the primary coil, the flux through the secondary coil will change.
Yes, sir.
And more specifically, if I consider the number of turns, so let it be n. Yes or
Yes,
no? So,
yes,
Yes.
and from here, if I remove this proportionality sign, now the thing will come into the play, that is m into IP. What is this m? M is the
sure.
coefficient
It's
of
constant.
mutual conductance, or this m is nothing but the mutual conductance.
Okay.
Uh, Mutual inductance, na? Why conductance?
Yes,
Mutual inductance. Is this clear to both of you?
Yes, sir.
yes, sir.
Okay, understood?
Yes,
Now we'll do the same things as we had done in the case of a self-inductance, that induced EMF in the secondary coil. Will it be EMF will be equals to minus of L time, or not L, minus of d by dt of n phi s? Yes or no? Will it be written
yes,
minus of d by dt of m into ip? This is ES. This is we are calculating it in the
yes,
secondary coil. So
Yes.
ES will be minus of m times of d of ip by dt.
yes,
Yes or no? Do you agree with this? So
Yes,
this
sir.
yes,
is
sir.
the term
Agree.
that we are getting it. Okay.
Yes, sir.
Yes, sir.
Okay. Now again the same thing, that we are just following the same pattern as we had done in the primary coil. Can anybody tell me that what was the second thing that we had done there?
We had found energy, right?
Seriously, we
No,
had
no,
done
magnetic.
till this point. we had done till this point in the last class, in the end of the last class. Yes or no?
Yes, yes, sir.
Now you have to remember that what you had done here in the first class, in the I mean
Oh,
in the initial of the starting of the class.
oh, yes, sir. We had so it was
This is
we had
something
for
the presence of
magnetic.
mind.
Yes,
Yes,
sir.
what we had done,
It was related magnetic field, right?
it is magnet. No, we had not done that.
No,
Acha, can anybody tell me that what is the first word that I had said here today?
That's weird.
first one. Good evening.
We had said the good evening. Other, apart from that,
Yes.
for the thing that we had done here,
No, sir. I'm not able to recall. Sir. I think we had done energy, right? No.
what we had done, we had for in the today's class, we had defined the self-inductance first.
Yes, sir.
So we'll define the mutual inductance as it is. In
Yes, sir.
similarly in the two-way only. Okay, that is
Okay.
coefficient of mutual inductance.
So,
Similarly, hmm,
for this mutual induction, right? So the primary current should be like greater than the secondary, right? I mean
yes,
the
exactly. It is going to happen always.
oh,
Okay. Otherwise,
okay,
what is going to happen? That if the primary coil is the smaller one, it can not link the same flux with the another one.
okay,
Okay.
okay.
I'm just keeping you very constrained and not making the doubts by myself. Otherwise, if I ask starting the doubts from myself now, you people will get
Mm.
confused for that. Because this is a
Oh,
very critical topic that should
mm.
be taken very in a very systematic way. Okay, because there
Okay.
is a lot of things to ask here. Ajay, tell me one thing, that while I writing the magnetic field here, I had not considered the magnetic field because of the secondary coil. Because of the secondary coil also there is some magnetic field induced in it.
Yes,
Yes or no? And that
yes, sir.
magnetic field will be somewhat in the downward direction because it want to reduce that magnetic field.
Yes.
Yes.
While writing the flux, I had not written that. Why? And nobody of you asked to me. This used to happen a
Oh,
lot of time in the not everywhere, but one or two students out of 100 students definitely used to ask this, that why we are doing this. Because see it very clearly, this is the thing that we should think about. Why I'm not writing it there?
Yeah, why?
Now why?
uh,
Can anybody tell
just
me that why I'm not writing it there? And I had not even, because see, I don't want to keep the things tedious here. Whatever I'm writing here, I know it's correct. But can anybody give me the justification that why I'm not writing it there? Even I have a lot to ask like this here in this particular topic, but I don't want to open it up here. I just want to finish it up today only. Why I'm not writing it there? See, because of the secondary coil, have I said it 100 times that this is the very small one? And
Oh,
from
so
this
yeah, yeah.
secondary coil,
it's
no.
negligible.
So first of all, listen it. It's not negligible. It's not negligible.
No.
What is happening? That because of this secondary coil, the B1 magnetic field that will be flowing in the downward direction, that will be in a very small area.
Yes.
Okay.
It will be only situated at the center. If you are already considering the ring to be small, and after that you
Mm.
are considering that magnetic field to be situated at the center only. Even that means even a smaller than smaller loop is situated at the center. Now,
Yes.
if you multiply this magnetic field with this area, because we are not concerned about the magnetic field, we are not talking about that. We are concerned about the flux through that particular thing. And if we're considering the flux, I must multiply that magnetic field with that small area. And if I multiply that, that will become negligible then.
Yes.
Understood? So this is the reason why I'm not taking that particular in the center wise manner. Okay, so let
Yes.
it be till here only. Then now we are going to define the coefficient of mutual inductance. Again, we'll do the same things. The first thing that how I had defined it, the first formula, that is n phi
N
s
N
equals to m
phi.
into n. phi s equals to m into ip. Okay, and the
Yes,
second thing that I'm defining here is es equals to minus of m times of dip by dt. Okay, and the next thing that I'll do here, that again I'll take out the again I'm taking the magnitude purpose only, because mutual inductance is not negative. Okay, it is positive only, so ultimately you have to report the answer to be in positive manner only. M equals to es by dip by dt,
yep.
and here what is happening, M will be equals
And
to
phi by IP.
n phi s by ip. Okay, so this is happening there, and uh, see, again, I'm going to just say the same thing, that in the primary coil, if the current is 1 ampere, then the mutual inductance will become numerically equal to the total flux through the secondary coil. Similarly, for this second part also. So, should I write it or I should copy paste it? I'm already having it with me. Okay,
Copy
I'll
paste it.
copy paste
Yes,
it
sir.
over here.
Yeah.
We'll save the time for this because that is just for the justification purpose and for to write it
Yes.
in your exam when it comes. Okay, and don't
Yes,
worry
sir.
about all these small things that I used to ask. That will be never being asked to you in the examination purpose. Okay, actually
Okay.
these are the very small concepts and very precise and something. Anybody who want to test that whether you know it or not, then he'll make the question accordingly. Okay, so it is just that is, you must have listened about the examination JEE Advanced.
Yeah.
This is the exam that actually used to focus over these small concepts and see that this is the real testing of the students, that whether they really know about it or not. Okay, so
Yes, sir.
actually that is being something asked being there, so not need to worry about it that it will be ever asked to you in the examination. Whatever being asked to you in the examination, you will get more than that here. Okay.
Yes,
So
sir.
this was the thing, and this was the mutual inductance, how we used to define the mutual inductance. What was the next thing that we used to define? Again, mutual inductance have the same unit as Henry. Okay, its unit, let me write it over here only in the top. Its unit is same as Henry. Okay, we are writing it over Henry only. Now, yes, what was the second, third thing? Recall it now. What we had calculated.
We had kept current as 1 ampere here, over here.
No,
Then,
no, yes, yes, we had defined it. We had just move away from that. Okay, move ahead of that.
yes.
We will define it. Okay, I had already defined it verbally. I'll copy paste the statements over here, and you will get it over there in the notes. Okay,
Okay, sir.
just what the next topic we had done in the mutual inductance?
Energy. Right?
Energy. Before that, yes, Vijan, you can also try.
Yeah, we are finding the L.
Yes, we are
Cell
finding the L.
reduction.
So
Cell
that
reduction.
means
Yeah.
now we'll do the calculation of M. We'll do the calculation of M. Okay, that is the mutual inductance. So we'll calculate the mutual inductance, that how we are going to have. Okay, so we can calculate it. So first of all, see, actually what is happening is it depending over the mutual inductance is depending over the flux. Okay,
Yes.
so it
Yes.
actually depends the geometry of the coil, that how the two coils are being kept. I cannot randomly take any coil and can ask you that what will be the mutual inductance of that particular thing.
Yeah.
Okay, so first thing that mutual inductance depends on. First thing that we are going to see here is that mutual inductance depends on. Depends on. So the first thing over which the mutual inductance depends is geometry of the coil. Geometry. Geometry of the coil. Okay. Geometry of the coil, I mean the from the geometry of the coil, like it is the square coil, it is the rectangular coil, or whatever it is. Okay.
Yes.
The second thing that we should consider about that relative geometry of the coil, that how the two coils are being are kept there. Can you understand that?
Yes.
Because the
Yes, sir.
way
Yes.
we'll
Yes.
Yes.
keep that two coil, that will going to defend the mutual inductance. Okay, so what we
Yes.
should write? Relative orientation of two coils okay. Now
Yep.
tell me that when they will be parallel, when they will be parallel, then do you think that the mutual inductance will be maximum flux will be linked from one to another? Yes or no?
Yes.
So
Yeah.
yeah,
The maximum flux will be linked from one to another. So what we can say that if the two coils are parallel, then it will be maximum. If two coils are parallel, it is maximum. And what the thing that I can write here, that if two coils are perpendicular, it is minimum. It is minimum. Okay. What the third thing it depends on? It depends on number of turns. This is a very easy thing that we should know about. And the fourth thing, permeability of medium. It will depend on permeability of medium. Understood?
yes, sir.
Okay. Now we'll do the calculation of the mutual inductance of a particular thing, and then we'll see that because we cannot calculate it randomly. I give you one coil like this, I give you another coil like this, you'll not be able to do so. Okay. So you
Yes.
must see the process that how I'm calculating it, and you'll see that only this was the thing that was being asked to anywhere. First of all, we'll do that, and let's see. Okay. So this is one of the coil that I'm taking here, and there is one of the another coil also. Let me draw it with some another color so that you people should understand. Okay. So this is the another coil. Can you see the two coils here? One is over the another, one is inside the another.
Yes, sir.
Yes or no?
Yes.
Okay. So if you can see it, so we will write some of the things over this. Let's say in the smaller coil, in the black one, it is the current is I1. In the bigger one, the current is in the red
I2.
one, I2. So let it be like this. In the second one, it is I2. So can you understand, distinguish the two things now that I'm writing over here?
Yes, sir.
Yes.
Okay. So let the length of both the coils to be L only. Let the length of both the coils be L only, and let the number of turns, I had drawn the number of turns to be different. So let's say the small, this red one is having N2. Okay. So let it write here only. And for the smaller one, let it say it is having the number of turns as N1. Okay. Understood?
Yes, sir.
Yes, sir.
And that's it. Okay. So should I write it separately also?
No, that's fine.
Solenoid 1, and it is solenoid. It is the solenoid one. It is a solenoid 2. So what I am writing over here is, let's say it is having the current I1, it is having the length L, and it is having a number of turns N1. It is having the current I2, it is having the length L, and it is having the number of turns per unit length to be N2. Okay, so what is the total number of turns? That is N1 into L. And what is the total number of turns here? That is N2 into L. Yes or no?
Yes.
Yes, sir.
What is the area? Let's say pi R1 square, and it is pi into R2 square. Okay. So what I am doing here is that this is very small. This is what I'm taking. This I'm taking to be very small this time. If I'm taking this to be very small, then we are going to calculate the flux again. Okay. We are going to calculate the mutual inductance. So do you agree that because of the magnetic field established by I2, That means flux in 1. Flux in 1 is directly proportional to the current in 2.
Yes, sir.
Yes or no? Flux in 1 is directly
No.
proportional to the current in 2. Or what I can say that the total flux is this. Yes or no?
Sir, what?
So flux 2, no?
Hmm?
Flux 2 is like directly proportional to flux I1. Because I1 is the smallest one.
I1 is the smallest one. Yes, I1 is the smallest one. So, okay, I had taken it incorrectly, or I had taken it correctly though.
Uh,
What is the issue in this?
oh,
The
yeah.
Because
Yeah.
of the current in 2, the flux is established in the 1. Do you understood
Yes,
Oh,
this?
yes. Yeah,
number two
oh,
is the bigger
yes.
one, right? Okay.
Yes. Did you
Yes,
Yes,
sir.
understood this?
okay.
That the magnetic field is passing in the smaller coil,
Yes,
and
sir.
Yes, sir.
that magnetic field is established because of the bigger coil. Because of the bigger coil, the magnetic field will be
Yes, sir.
in the center. It will be constant.
Hmm. Yes, sir.
Okay, understood. Because if this is
Yeah.
the bigger coil, it will establish the magnetic field in the center to be constant. Whatever will be the boundary, we don't know about. We only know about the magnetic field at the center only. That's why we are taking the magnetic field because of the two only. Okay.
Yes, sir.
So what I can do, n phi 1, if I replace it, I'll place the M12 here. M12 here. What is M12? M12 is the mutual inductance. It is the mutual inductance in solenoid 1 due to current in 2.
Yes, sir.
In
Yes, sir.
solenoid 1 due to current in 2.
S-
Solenoid 2. Is this okay to you?
Yes, sir.
Yes, sir.
Okay. Now do the rest of the things will be very easy for you. Now tell me, N, what should I write in phi 1? I should write the magnetic field into the area.
Yes,
Area is
area.
that is pi into R1 square. Yes or no?
Yes, sir.
Yes, sir.
What is the B should I take? What is the magnetic field at the center of the solenoid? We know it's mu naught Ni.
Mu naught and I.
Yeah.
But what should I take here now? This is the real task for you.
Oh, you know what I do.
Mu naught I2
Uh,
exactly. And N,
Yeah,
N is taken as?
yeah.
N is into N2, right?
Yes, mu naught
Oh,
N2
yeah.
into I2. This is the magnetic field established because of I2 current, na? So we'll take it as mu naught N2 into I2. Okay.
Okay.
And that will be equal to M12 into I2. Is this okay?
Yes, sir.
Yes, sir.
And this N, this capital N that I'm writing here, what is its religion? It's N1 or N2?
Uh,
It's equal on both sides.
Is it equal on both sides? See it here. It's N1
No,
into L and it's N2 into L. So what is the capital N? It's N1 or N2?
the end, you know.
It's N1. Why
oh,
N1? It
yes,
is the
yes, because
flux,
flux
total
is in
flux with the
N1.
1.
Yeah,
Oh, yeah, yeah. Mm.
Okay, so
Yes,
this
sir.
is that's why I was saying that just I'm taking you with a very in a very slow manner. I2 will be cancelled out, and what the M2 will I get? M12 will I get? M12 will be N1, and for the time being, let me write it properly. Mu naught N1 N2 into A1. Okay, is this okay?
yes,
Okay.
yes, sir.
And if you want to do somewhat better, so you can mu naught N1 instead of N1, you
Square.
can use N2
Oh,
A1
N1 into
into
A1.
L1. Now this time you can't do the square here.
Yeah, because it's different. Yes.
Okay, M12. So it is somewhat like this. So is it looking like mu naught N square into volume, but
Yeah.
with somewhat a little changed one? This N square is not literally N square, it is N1 into N2.
Yeah.
Yeah.
Okay, so this is something that is we had calculated the M12. Similarly, right, see, you can represent it in terms of capital N also, but I'm not doing it here. You already know that what is this small n1? This is capital N1 by L, and small
Yeah.
n2, this is capital N2 by L.
Yes.
Okay, so you know it, you can
Yes.
do it, but I'm not doing it over here. See, the most important thing of writing here is this particular expression. Actually, I should really tell you that this is the one expression. If you understand this, you will not face any kind of a problem over another things. Phi1 is the flux through 1. And what is the flux through 1? This is the magnetic field due to established by the 2 into area of the 1.
Yes.
Yes, sir.
Understood? This is the thing that you should remember and you should know about. This is the M12 we had calculated. Okay, is this clear?
Yes, sir.
Now just understand that if we want to calculate the M21, M21 will be, what will be the M21? Mutual inductance in solenoid 2 due to the current in 1.
Yes.
Okay, understood? So what it will be? It will be what it will be. If you this time what we are going to say, N2 into phi 2 is directly proportional to the current in I1.
Yeah.
Yes. Yes, sir. Sir, can't hear you, sir. No. No, sir. Can't hear you.
Now can you hear me?
Yes, sir.
Yes. Yes.
Let's see what happens. So this is the thing that we had seen. So now this time if we do N2 into phi 2 will be equals to, this time we'll write the M21 here and I1 here. Is this correct?
Yes, sir.
Yes.
Is this okay to you? Now tell me one
Yes.
thing, that what is phi 2 this time?
Uh,
Phi 2 is the
uh,
flux in
In the
the
second loop. In the second
yeah.
loop.
second row. Yeah.
Okay. In the
Yes.
second loop. So you should multiply the B and A. Okay.
Yeah.
But tell me one thing. If you multiply the B, what kind of B you should take here?
Yeah. You not N2 and no, you not N1 and I1.
Yes, this will be B1 actually. And
Yeah.
area, what is the area should you take here? This is the A1 area. Still you will take the area A1. The reason behind that, because that is the smaller one. Understood?
Yes.
Because of the larger one,
Yes,
we
sir.
are not we cannot calculate it. We actually from the larger one also still the same flux is there. Okay. Now M21 into I1. This is the now the things are over here. Okay. Now what the next thing we'll get? N2 instead of B1, what we should take? Mu naught N1 into I1 into A1 equals to M21 into I1. Is this okay?
Yes,
Yes,
sir.
sir.
Now just cut the I1 from both the sides. What the M21 you will get here? You will get the M21 to be equal to mu naught N2 N1 into A1. Is it okay?
Yes, sir.
And still, if you go mu naught N2 N1 A1 into L. Is it okay?
Yes, sir.
Yes, sir.
And if we write it a little bit more properly, what will I get? M21 equals to mu naught N1 N2 A1 into L.
Yeah.
So this is the final expression for M21. And from here, what can we see? We can see that M12 is equals to M21.
Yep.
Yes or no?
Yes, sir.
Yes, sir.
So this is the thing that we had got here, and we used to say it right like this, that M12 equals to M21 equals to M. This is one of the very favorite question of the examination, that they used to ask, that uh, derive that M12 equals to M21 equals to M. Okay, understood?
Yes, sir.
So this is
Yes,
something
sir.
that you will get it over here. And that was the final thing that I want to say here about the mutual inductance. And this is the final all over. Okay,
Yes, sir.
the mutual inductance. That's all the today's topic about the mutual inductance. And you should remember all these final expressions that we had calculated. Mu naught N1, sorry, mu naught N1 N2, A1 into L. Okay,
Yes, sir.
that's all about this class. And let us do some of the questions over here. Okay. Uh, related to some of the. Let us take a small question over here.
Sir, chapter is not over yet.
Yeah, chapter is over. Chapter is
It's
over
over.
now.
Okay, sir.
Okay, chapter is over now. I'm just giving you some of the questions as we cannot start the next chapter now. We will
Yes.
start it in the next class only. Before that, let's do some of the good questions over here. Suppose that uh, suppose what I'm doing here is that let us say that I had change this area. Okay. Suppose that I had established. Now the chapter is over. I'm just giving you some questions.
Yes, sir.
Okay. Suppose this is a magnetic field that is established over here. This is the B magnetic field that is being established over here, that is pointing inside. And let us say this is the semicircle with radius. Let's say the radius is R over here. The radius is R over here. If the radius is R over here, and suppose that we had given a velocity, this this is the velocity that we had provided it to it. So can you tell me that what will be the EMF induced over here? Solve it. Suppose I'm marking the 2 points P and Q. What will be the EMF induced in this case?
Uh, Sir, magnetic field is going in the plane, right?
Yes, magnetic field is going inside, inside the plane, and you should solve it over
Okay.
here.
So this is, you have to use the motional EMF, right?
Yes,
Or,
motional EMF questions. It is
okay.
depending over that only. Okay, solve
So
it.
will it be
Yes,
just BLV?
be, just try to solve it. I'll let you know about it. See, I'll tell you the answer over here. Whenever we are calculating, you people are able to hear me now?
Yes, sir.
Yes, sir.
Okay. So whenever we are calculating the EMF, the length, the actual length doesn't matter. The perpendicular length, that is the perpendicular length to the velocity. When you write this formula, na, that EMF equals to VBL, that you write this formula that EMF equals to VBL. In this L, what is this? This is. Are you able to hear me?
Yes, sir.
Yeah, we can hear you, sir.
Okay, just a second. Yes. Are you?
No, sir.
Yes. Hello. You are not able
Yeah,
to hear me?
Yeah, yes, sir.
yes, sir. Able to.
Okay. So whenever you have to take this L, this is perpendicular to velocity. Okay. Understood? So the
Yes, sir.
length that is perpendicular to velocity here is this particular one. That is nothing but
Yes.
2R. So the EMF will be VB into 2R. This will be the final answer. Understood?
Yes, sir.
And even I had said you to. Okay. Okay, just tell me one thing, one more thing, that this is going to happen over here. If what I'm doing here is that instead of this, I'm just writing the question directly over here. Okay, I'm not beautifying that question. Suppose that I had taken the length rod somewhat like this in this shape. Rod somewhat like in this shape where this is a semicircle of radius r. This is the semicircle of radius r, and this is taking this length to be L. I'm taking this to be L. And suppose this time I'm rotating it. I'm this rotating it. So what will be the final expression for this? EMF will
So
be induced here. Okay.
rotating like about its axis or
About this particular, this is the pivot point where I
okay.
had just
Yes.
fixed it over this, and I'm rotating it over. Magnetic field is somewhat like this. Yes, solve it. Now, what is going to be the effective length this time? This time, the effective length will be this. The reason behind that, because what is actually happening, that this particular length, suppose that if we consider this whole length, if we consider this whole length, so
Oh,
this is a rod which will establish a potential difference, okay or not? And can you tell me
yes,
that
sir.
which side will be at the higher potential? Where should I make it like this, or should I make it like this?
Sir, over here, which direction is like the V velocity over here?
You can see it. I just drawn it. This is the omega that I'm
Oh, I
rotating it.
didn't see. Oh, yes. Okay. So it will be the first option.
It will be the first one. Can you see it, Rajan?
Yes, sir.
So this will be the first one. It will be somewhat like this. But for this small length, how will it be?
So for the small length, what I
This
didn't get the
small
question, sir.
length will, for this small length that I'm talking about it. How will it be
It will be
located like?
this.
Oh,
It
So
will be the
that.
same.
same, right?
It will be the same. But now
Yes.
tell me, are these batteries joined somewhat like this?
Yeah.
So actually, this small portion is the reducing one. The one which had the small EMF induced somewhat here will be the same EMF induced somewhat here also. So they will cancel out each other, and this will be the effective length this time.
Sir, I didn't understand.
See what is actually happening here. What happened is we are over with the time also. This is one of the good question that I always used to see. Whenever we had taken the rod somewhat like this,
Yeah.
for this bigger one, you can, okay, just remove all this thing. For this smaller one, can you define the EMF? Yes or no? This length
Yes.
will cancel out each other. One will be this,
Yes.
another one will be this. So they are not
Yes.
just what you can see, they are joined somewhat in this manner.
Yes.
Yes.
So they are canceling out each other. So ultimately, the EMF is being
Yes.
induced by this particular diagonal length.
Yeah.
Okay.
And
So the EMF will be this diagonal one. That will be EMF equals to VB into L dash, where L dash will be this hypotenuse. This hypotenuse will be what? Under root of L square plus 2R ka whole square.
okay.
Okay.
Yes, sir.
If you want me, so that I can give more light over this particular thing in the next class also. But till now, just keep it like this. You understood now that what I
Yes, yes, sir.
am
Understood.
talking about here, that actually
Yes.
we have to take in the first question we learned that you have to take the length to be perpendicular one only. Okay,
Yeah.
so let it be till here only. And from the next class, what do you want? Should we start our next chapter? That what actually the chapter should we supposed to start?
we were doing current electricity. Yeah.
It will be current electricity or the magnetism. I think magnetism matter is the very small chapter. You can do it at your own also, and there is nothing
Yes.
too hectic or the conceptual thing that I should explain it there. Okay, that is mostly
Yes.
theoretical kind of a things. So if you want it, so you can do it at your own also for the school examination. And we should
Yeah.
start the current electricity, continue our current electricity if you say yes to this.
Yes. So I thought we could have one class with like where you could teach us
With
some
like questions
or
of that.
questions. Yes,
So
some like important.
yes. So which chapter of the question do you want?
Moving
Moving charges
charges, AC current,
and
Second
this
is AC. Third
AC,
is
and
EMI.
EMI. Yeah.
Okay, only all these three.
Yeah.
yes, sir. So magnetism matter, right? Only that diamagnet and paramagnet and ferromagnet is
Yes,
important,
that
right?
is something. All those things, theoretical things, are going to
Yeah.
happen all this. Okay,
Other topics,
so
yeah. Only that part is important on that, right? So like other
yes,
like
that
this.
part is important one, and some of the small derivations are also there. So actually, you can do it at your own if you find it
Mm,
anywhere. You can do it for the school examination. You can do it there. And I
yeah.
Yeah.
think with we should discuss the questions over this particular topic in the next class. And after that, from the next to next class, we'll start with the chapter current electricity. Okay.
Yes, sir.
Okay.
Sir, is it possible to have the classes on Friday and Saturday instead of Saturday and Sunday for next week or no?
For Friday and Saturday. Uh, okay, I'll let you know about it. Okay,
Okay, sir.
you'll get the notification for that. Okay.
Okay, sir. Thank you, sir.
Okay.
Thank
Okay.
you.
Thank you so much. You can leave it.
Thanks.
Thank you.
Good evening, everyone. Yes, Aman, Humaira, can you hear me?
Yes, sir.
Yes. Both of you, please answer me that whether you can hear me or not.
Hello?
Good evening, everyone.